Hi, Santosh, can you hear me?
Yes, sir. I can hear you.
Hi, Sagar. Yeah, sorry, I was a little delayed. I had another meeting just.
Okay, no problem.
Rushing out of that. So let me just share my screen. Can you see my screen?
Yes, I can.
Okay, excellent. It's in full screen mode. Now you can see that.
Yeah.
Excellent. Thank you very much. All right. So good morning, everyone, and I'm happy to be back, and I hope that you are happy to be back as well. We did mention yesterday about this, and we finished by saying that solar atmosphere is structured, and the different layers of the atmosphere, which is photosphere, chromosphere, transition region, and the corona, are all magnetically coupled. Now, what we will do is we'll go into the atmosphere and talk about structures in a bit more detail, and then see how actually we move forward towards other activity, solar cycle, and so on. So this is just a single snapshot. If I put it together here, this is an animation put together by taking different observations. So you see sunspots, which shows magnetic field, of course, and that's why it is dark. And then you also see flashing different upper layers of the atmosphere. So this is chromosphere. This is observed in helium 304, helium-2 304. Now this is an X-ray image, which is emitting at 2 million degrees. And essentially it tells you that the regions where you have a strong sunspots, that means there is strong magnetic field. And that is where most of the structures, the brightest structures you see within the solar corona and in the upper layers of the atmosphere. Now, so far, since we have learned this, we know that we have interior, then we have photosphere, which is about 500 kilometers thick. And then we go up, we get chromosphere, and then we go higher up, which is the transition region and the corona. Why it is called transition region between chromosphere and the corona is reflected in this plot here. So what you see here on x-axis, you have height. On y-axis, on the left side, you have temperature, right? What you're seeing that if you go inside this direction, then you're going inside the sun. And of course, the temperature will increase because that's where it has to reach to 15 million degrees for the nuclear reactions to occur. But as you expect that when you go away from the heat source, the temperature is going down and you will reach a location where you have temperature minimum. In usual sense, the temperature should just falls down, right? Because further away you go, it will just be much cooler. What happens at the bottom of the chromosphere, that is where you start the chromosphere here. At the bottom of the chromosphere, essentially, we start a region where the temperature start to increase. And now this depends on different kind of models you take, different opacities you take, and so on. This is very representative, very, very approximate model. And this is one-dimensional model considering that the solar atmosphere is plane parallel, stratified. That means like, sitting in a room and the whole room is in thermal equilibrium. You go from one location to other location at the same height, the temperature will be the same. That doesn't work in the solar atmosphere. But if you consider the whole thing as 1D, then you can just, of course, make such kind of statements. So what is done is just by 1D, and what you're essentially seeing that the temperature starts to increase, and then it hits the bottom of the transition region, which is this here, and the temperature suddenly, which goes from about 10,000 degrees to about 1 million degrees and beyond, and it goes into the corona. And that thickness is roughly about 200 to 300 kilometers, which is called the transition region. And then in the corona, the temperature is still further increases. You can go all the way up to 2 million degrees, right? The opposite thing happens with the density, and density, of course, falls down, when you go away from the sun. And what essentially you see is temperature is just decreasing, of course, but it decreases by about 2 to 3 orders of magnitude.
Durgesh sir, sorry for listening. The slide is not movable.
Not movable. Can you see the plot?
No.
what slide are you seeing now?
Yellow colors.
Okay, does it move now?
Yeah, right
now. Okay, now did it change?
Yeah.
So you see white and black graphs.
Right, graphs. Right.
Okay. Right. So thank you, Sagar. Okay, then my couple of minutes are lost. But you heard me. Every one of you heard me what I was saying. All I was trying to say is that when you go into the corona or at above the chromosphere, the temperature changes from about 10,000 degrees to it gets around to 1,000,000 degrees. Right, and similar thing happens with the density, but density doesn't start increasing. As you see, the density starts decreasing and keeps decreasing, and that's what you should expect. We're going away from the sun, but within the transition region, when the temperature changes from 10,000 to about 1,000,000 degree, of course 1,000,000 is here, so this is different model, as I said. Within the same distance, the density also changes by 2 to 3 orders of magnitude. And that is what makes this region is a very sudden change, and that's why it's called a transition region. Some people call it the interface region between the chromosphere and the corona. And as we know now that this region is, although very thin, it is very, very highly dynamic and plays a very important role in the solar atmospheric dynamics. Now, as I said, this is a 1D model, which is very, very approximate. It's not applicable everywhere, but it still gives you illustrative idea about how the solar atmosphere would have structured. We can now take images that are different, and it will show you that the atmosphere is not in a plane parallel atmosphere. Now, the most important question, which relates to many other facts like X-ray radiation, ultraviolet radiation, its effect on the Earth atmosphere, in the ozone layer, and the sun-climate relations, and everything is just essentially governed by these kind of photons, which are ultraviolet and X-rays, which are coming from these regions from the upper atmosphere of the sun. Now, this is an image taken in visible light from Swedish Solar Telescope, and what it shows is a sunspot, right? So what you see, there's the dark region of the umbra, and this is penumbra, and that is granules. This I showed you earlier also. So what essentially this means, there's a very strong magnetic field here in the umbra, which is a kind of vertical field lines, like a bundle of flux tubes like that. And when you're going away, the bundle of the flux tube, outer periphery flux tubes are just kind of sliding into the surface. They become parallel to the surface, and they merge within the photosphere itself. Well, and since the direction is vertical here, there is no convection, and the plasma doesn't penetrate through and doesn't come out, and that's why it's less dense as well as cooler, and therefore this appears dark. Whereas here, these are the granules, and now the plane parallelity, depending on which structure you are looking at, the structure or the ambience is very, very different, right? Even if you go further, this is in quiet sun region, and these are taken in G band. And what you have here is like these bright points here, very, very bright regions here, which are forming within these dark lanes, right? So if you look at this kind of region, dark lanes, they are of course dynamically evolving, but these regions also host these really bright, strong, bright patches. And they are the first signatures of the magnetic field, which are available within these dark lanes. And that's what eventually then they collide together, combine together, they make larger scale field. Even if you go higher, this is taken in H-alpha image, a very high resolution, again with the Swedish Solar Telescope. And you can play and see, this is chromosphere now. So earlier the two images were photosphere, this is chromosphere. And as you can see, there are a lot of structures evolving in all kind of fashion you can imagine. And each of these structures could be sort of showing very different dynamics. If you concentrate on this part here, and if you concentrate in this part here, you see that there are fibril kind of motions which are connecting. There are structures which are appearing, and they are being dynamic. So earlier this structure was not that dark, but now it becomes darker with time. Right. So the whole dynamics, just by changing the filter, that means just changing the atmospheric layer you are going, it just changes the whole dynamics in the Earth atmosphere. And all these structures are still topic of hot debates, that how do they form, what is their dynamics, how actually they play a role in heating and sustaining the upper atmosphere of the sun. Even if you go even further, this is under animation. If I can run it. Sagar, does it change my slide? Hello? Hello? Can you hear me? Okay. Right. So you can hear me. Very good. Right. So this, again, I was showing. So let me just get away from these animation. I just wanted you to get fascinated by these. So that what you are essentially looking at, depending on the structure you are looking, depending on the region you are seeing in the solar atmosphere, the atmosphere is not plane parallel, so that 1D thing would not work anymore, and therefore you have to start modeling different structures in its own entity, and that makes the life much more complicated when it comes to modeling different specific structures, because the scales of physics are very, very different. You have to consider if the plasma is in thermal equilibrium or not, and then if it is not in thermal equilibrium, then you have to start introducing much more complicated physics and so on. This is going even further. So this is taken in calcium-2 from Hinode SOT observation, and what you are essentially seeing here is that's the limb, and these are spicule-like material which are wobbling and swaying motions. People call it like they are showing this motion because of Alfvén wave propagating upwards, but it still is an open question that what actually form these kind of spicule structures, and why actually they are oscillating, and how much energy do they carry. I mean, one of the most important questions people are trying to figure out is what are the sources for this energy, which is going and heating up the upper atmosphere, and how actually you transport it. And source and transportation is one thing, but then also how you dissipate, because you have to essentially heat the plasma to understand and explain the coronal heating problem or the solar atmospheric heating problem. The other things you see here is this particular structure, as if you can see that there is a slab of plasma which is just hanging in the atmosphere and is supported against the gravity, because the gravity should just pull this plasma down at the surface. But as you can see, this is as if you're taking a pen. If you can see my hand, it's a pen and it's just lying in the atmosphere, right? So if the gravity is working, it should just fall down unless you're providing a support against the gravity. And what we know now is that this magnetic field, which you measure on the surface, they have lines of forces going into the atmosphere, and those magnetic forces are providing the support against the gravity. So if you have a magnetic field structure, as if you have a helical field, then what will happen in a helix? The tension force will work upside, and the gravity will work down, and therefore this will be supported by the tension and the gravity, and the plasma can just stay there. Now it's just not a stable system, because as you can see, the whole plasma is just moving. There are trains of plasma which are going in this direction. Some plasma trains are going in this direction. So there was a paper by a Japanese colleague, Okamoto-san, who actually figured out that these are kind of Alfvén mode. So if you look at MST waves, there are 3 different kind of modes: fast modes, slow modes, and Alfvén modes. And they are the magnetic modes. And he detected signatures of these magnetic modes which are propagating along these structures. Then what you also see that there are some plasma which is just falling down on this. Not everything is just supported. And that is essentially because you have a cooling catastrophe. Because if the density becomes very, very high, it just gets into the cooling phase, and then it just cools and drains along the field lines on the surface of the sun. It's called coronal rain or something, if you like. Then if you go even higher, that means changing the temperature. I showed you this yesterday, and what you have is just evolving coronal loops, right? So these structures are evolving at a minute. So what are these structures? They are nothing but essentially your magnetic lines of forces. So you have 2 polarities, plus and minus, and if you draw lines of forces, these are lines of forces, and the plasma is just trapped in because it's a fully ionized plasma, as I explained earlier. And because of that, you see those field lines. Otherwise, you don't see magnetic lines of forces in general, and they are evolving on time scales of minutes to hours. And as you can see, these are the regions which are much brighter. That means the heating is much more pronounced in these regions. And that's why you say that the source of that energy is magnetic field. Now, how do you transport the heat into the through magnetic field into the upper layers of the atmosphere? And how essentially you generate so that you heat the plasma and you see the hot plasma is a sort of question which people would have to figure out, and is still trying to figure out. This is something I showed earlier, I think, and you have this huge ball of plasma which is just sitting on the surface and just decides to erupt on one particular day. If I have to put this Earth on a scale, then it will be a tiny dot around here, and that essentially tells you that the whole plasma just comes on the Earth. It will just engulf us. And the good thing is that the vastness between the Earth and the sun is huge, and only a tiny part just comes in. But still, it can create, if it is geoeffective, various effects, as we discussed yesterday. This is just flare, so it's just a sudden brightening appearing on the surface of the sun. There are 3 different colors. They're representing 3 different temperatures. So you take 3 telescopes and take simultaneous observations and put them together by taking different colors. This is, of course, ultraviolet, and ultraviolet color we don't know. We can't have color because color is only defined for visible. So what is done here is, just to visualize it better, 3 different wavelengths are given artificial colors: red, green, and blue, and that's what is plotted here. And what it shows that any structure you're looking at is highly multithermal. At any given point, you have plasma at all these temperatures, at least 3 of them, which are shown here. But now we know that it's any point on the sun, along the line of sight, you have multiple temperature structures, and everything is multithermal. And the further observation you get, now we know that the moon comes and blocks the disk of the sun, and only then we see the outer atmosphere. We understand the physics of it. Then what we could do, we could create our own eclipses. And once we found those eclipses, then we can start seeing what's happening outside. And that's what is done here. So there was this instrument is called coronagraph, right? So there was a coronagraph. Actually, there were 3 coronagraphs, but this is only shown from the 3rd one, which observes from about 3.6 solar radius to about 32 solar radius. And this is what you see, all these stars in the background. And this is the equatorial belt where you have all these streamers, but you also have a lot of ejections, sudden ejections, big blob of plasma which is going out in the interplanetary medium. And that is called coronal mass ejection. Now, in addition, what you also see, there is this comet which is coming into the field of view and just grazing and going away. What you see in this, if I can pause it at some point, that it has two tails, right? Any comet has two tails. One is the dust tail, which is this thick here. And the other is the ionic tail, which is this one, right? And if you observe this and monitor with time, what you will see, while the comet is grazing, the dust tail is not getting affected, whereas this ionic tail will always point radially outward when it goes out of, when it grazes and goes along this, right? So if I just move it further, as you can see, that this comet tail is always pointing radially outward, the ionic tail. And that essentially tells you that if this dust tail is not getting affected, and this ionic tails are getting affected, that means that there is ions and charged particles which are being ejected from the sun at all times, which are affecting this ionic tail. And that's the first evidence for solar wind, and which is nothing but just the charged particles which are propagating away at all times from the sun into the interplanetary medium. And that came from Behrman a long time ago, but now we have direct information and observations of this solar wind. Okay, and as I earlier also mentioned, that now this is a newer observation. We just start it again. What you see here is just the magnetic field measurement at each point on the sun. So these are the regions with a stronger magnetic field, and then you have all these salt and pepper spread over on the solar disk. Now, if you closely monitor this particular region here, what will happen what we're going to do is we're taking images simultaneously at different height into the atmosphere just by taking different filters. That means showing different temperatures. And you would see that this particular region is showing all these activities. So if I just now imagine this, so there is some sort of eruption going on here, right? And then you see the same eruption is being seen in now at about 1 million degrees. When you go further, this is about 1.6 million degrees. Now look at the dynamics, how different the dynamics is. The whole structure is just this big here in this particular wave band, right? In this particular temperature, and just affecting the whole global structure in the atmosphere. Look at this. The way it is going out, just sweeping the plasma away from this, and you see much more dimmer regions around here, right? This is called Martin wave. So essentially kind of shock wave, which is just taking away, sweeping the plasma away along with it. Now, if you go even higher in temperature, which is now 2 million degrees, you see similar effect. Now you see the bright front moving much nicely here, right? This here. Now you're going 2.5 million. So you see this something different, not that clear signature, because all the activities you see, they are very sensitive to temperatures, right? So, and your filters are very sensitive to temperatures. So if it is emitting or absorbing at that, then only you will see it. Otherwise, you won't. Now here you are going up to 6.3 million degrees. And you see these hot loops which are forming around this here, these structures. And then again, sweeping away of the plasma. And now you are going 10 million degrees, which are showing these inside hot structures here. But let me tell you, these structures are seen in all these filters, right? So that means that there are different flux tubes or bundles which are emitting at different temperatures, and depending on the filter you are using, you are seeing such structures in those. Okay, and if I'm just going back, this is happening in the region which is very strongly magnetized. Now you can always ask a question why it is not happening here and here. So that is why, that is what is the question is, that can we say by looking at these, can we say that which region is going to show these kind of eruptions which is being seen in this particular region? And if we can say that, then one of the problems related to the forecasting of eruptions, which has very strong effect on space weather, will be solved, right? We know that it is happening in the magnetic region. We know that these things, these large scale things do not happen in regions like that, except occasionally. But when and how exactly these things happen, we have some certain idea about those, but not a full understanding. Okay, now what we know is that we can measure magnetic field on the surface of the sun, and that is the photosphere. And we get the information about the distribution of magnetic field and electron density in the corona of the sun by taking into account the Thomson scattering. So why can't we measure magnetic field directly in the corona? We would like to do that because if everything, the whole dynamics is governed by the magnetic field, then it would be nice to have a direct magnetic field measurement within the corona, but we cannot do that. And the reason is that when you think of Zeeman splitting, what it does, when you look at a magnetized gas, and if you have a spectral line, which is magnetically sensitive, then what it will do, depending on the magnetic field, it will show a splitting of the spectral line. However, if the line is very, very broad, that means if the thermal width of the line is very large. And why would that be very large? Because the temperature in the corona is very, very high, 1 million degrees. Then the spectral lines you take, the thermal width of the line will be already very large, right? And the magnetic field, since the source of the magnetic field on the surface, if you go away, the magnetic field will be decreasing, right? Depending on you take bipolar or quadrupolar configuration, you can work out how much it will decrease. Now, if that decreases, then the splitting introduced because of the magnetic field in the corona will be very, very small. So your line is already broad, the splitting is very small, and therefore it's not detectable. And therefore it is very, very difficult, if not impossible, to measure the magnetic field in the corona directly. But it's not that we don't understand how the magnetic field, at least on the global scale, in the corona is. What we do, we know the photospheric magnetic field. And from there, considering that as a boundary condition, we can derive what the magnetic field structure should look like, right? And this is what is done here. So to compare with the eclipse, is done for the magnetic field which are on the limb side. What you see on the global scale, it matches very nicely. You can figure out these kind of field lines here, hair-like structures. They match very nice here, right? Different colors have different strength of the magnetic field. You also have this structure here, which is nicely matching, although not exactly, because you have these kind of much more complex regions, which you can see in the eclipse images, which are not reflected here. Whereas this here is very nicely matched. Look at this cuspy structure, which you can measure here. So there are drawbacks, but still you have an overall configuration of magnetic field, the way it is happening in the corona. The further drawback is that it is very difficult to look at the evolution of this magnetic field, because here we can take a sort of you can create an artificial eclipsing, and we can look at the dynamics of these structures, but this will take time and it's difficult to predict a real-time magnetic field map. Okay, so it is an ongoing effort to directly measure the magnetic field in the corona. And one of the instruments which is going to be on Aditya L1 mission is supposed to be doing that. Of course, it will not be able to do because the intensity is very small. So you'll have to do a lot of time integration to get enough signal to noise ratio to measure the magnetic field. Again, by polarization. So what it will do, it will measure different polarization in iron 13 lines. If you know the Stokes polarimetry. And from there, it will invert the direction of the magnetic field. But that will be a start, and further techniques has to be developed to try to understand and measure the magnetic field in the corona. Now, I said that depending on where you are in the solar cycle, so if it is solar minimum or solar maximum, the temperature in the Earth atmosphere. So if you're doing the solar minimum, the temperature would be about at this height at 150 kilometers is going to be about 500 to 600 Kelvin. Whereas if you go to maximum, then at the same height, the temperature will be about 1000 Kelvin. So you're talking about a difference of 300 to 400 Kelvin. What it will do, the Earth atmosphere is a gas, essentially. So it absorbs, the temperature increases, and therefore it expands and sort of shrinks with the solar radiation. And because of that, it creates a space weather effect, which destabilizes all the space telescopes which are within the Earth's atmosphere. And you have to provide a booster sort of thing every year to sort of keep the orbit intact. Okay, so let me summarize this before we go to the next point. I hope I've made it clear that sun is an important object to study. And it's an object that provides clues to our understanding of the farther universe because it's the closest astrophysical object. And so magnetic field plays a crucial role in heating up the upper atmosphere. And the sun's magnetic field plays a crucial role in large-scale eruptions, flares, and coronal mass ejections. But the question is that how and where the magnetic field on the sun is generated. And I mentioned that there's a dynamo, but how actually does that work? Now let's look at that in a little bit, the sunspots and solar magnetic field, and that will also take us to the solar cycle question. As I said, so this is granules and taken in G band, and all you see is that's the generation of these magnetic fields, which are localized within these dark lanes within 2 granules, for example. So sunspots, we talked about this. You have these dark regions on the surface of the sun. And it was discovered by Galileo, was one of the first one to use a telescope to look at the sun, and he discovered sunspots. Of course, I think there was some record of Chinese scientists having already discovered sunspots, but this was the first record came from Galileo. And these are his own drawings. And what he also figured out was that the sun was rotating on an axis, which is, so sun's rotation axis was tilted 7 degrees by the magnetic axis. And that is what is shown here. So if the equator will be here, the current age equator, because tilted from the equator by 7 degrees. And by looking at these structures, you can work out the rotation period, and it was figured out that the equator of the sun rotates faster than the pole of the sun. And here, if you track a region, it will complete a cycle in 27 days, whereas here it can take up to 35 days. In addition, he also looked at Jupiter's moons and discovered those and so on. This was his house. But if you look at the same sunspot with high resolution, then this is what you find, right? I showed you some pictures earlier. We have the umbra of the sunspots. They can be very, very complex. Of course, you don't see such kind of complexity in these kind of drawings because they were just drawing and they were taken on a plane of paper. But now you see very complex structures which are shown here. They are umbrae, penumbra, granules, of course, and then you also have these bridges which are connecting from one side of the umbra to the other side of the umbra into the penumbra, and they are called light bridges. If you look at this, what you essentially find, again, very high resolution observation, granules outside, and what else I wanted to point out? If you see this clearly, what you also see that these features here, they are moving with inside the sunspot. And if you do a Doppler imaging of this, so look at the line shift, what you find that is that these features are not going inside the sunspot, but rather they are going out. The gas is moving out. Since they go out slower than these granulation structures, that's why in relative terms, they are looking as if they're going inside. And that is what is called Evershed effect. And that was discovered from our Kodaikanal Observatory in 1808 by John Evershed. Now, if you count all these number of sunspots, what you find is, I have to move this. So this is done from 1870. Now it goes back all the way to Galileo time and even before. What you see here is that, okay, let me just tell you what is plotted here. So the year is plotted on x-axis, and the average daily sunspot number, that is the percentage of the visible hemisphere. That's why it's coming in fraction. Otherwise, the number cannot be in fraction. Is plotted on the y-axis. What you see is that there are times when there are almost no sunspot on the surface. At the same time, there are times when there are very large number of sunspots on the surface of the sun, right? And that too, that changes from year to year, right? So what essentially this plot tells you that there is a time when there is no sunspot, and then slowly the number of sunspots starts to increase, gets to a maximum, and then decreases. Then there is no sunspot, again goes to a maximum, then it decreases. And that happens roughly within a period of 10 to 11 years, right? So it's not, of course, 11 years on a regular cycle, but roughly it's about 10 to 11 years. And that is what is called solar cycle. That the number of sunspots start from no sunspot to the no, and finishes with no sunspot is one cycle. And that is the sunspot cycle or the solar cycle. Okay? That is just the counting. What you also see is sometimes the numbers can be very, very large. And if you have very, very large number of sunspots, that means there is a large magnetic field on the surface of the sun. Therefore, the sun is going to be much more active. So one cycle here is given a name. This is the 12th cycle, then 13th cycle, 14th cycle is being counted from Carrington days. And what you get at the moment, we have already started our 25th. So this was 24th cycle. We've already started 25th cycle of the solar or sunspots. Okay. So the more number of sunspots you have, then the sun becomes much more active. That means you have more eruptions and more ejections and so on and so forth. What is shown here at the bottom panel is now we can identify where the sunspot is, and we can define a coordinate system. And I explained that yesterday, that you define the coordinate system as if you have a disk, and the north 90 degrees up, south 90 degrees down, east in this direction, and west in this direction. And we can mark the latitude and longitude of each sunspot we identify. We also can mark the area, but don't bother about the area. The color here is showing the area of the sunspots, but don't bother about it. what we want to see here is, again, the time and their appearance, the location of their existence on the surface of the sun or the disk of the sun. So if we start at 1880, as you can say, when the sun is starting its cycle, the sunspot starts to appear at higher latitude, around 30 degrees, 40 degrees towards the north, and the same time in the south. And then as and when it is progressing upward, then it's just migrating towards the equator, both of these. And then again, when it goes to the minimum, all the sunspots finished, and they have all migrated and joined together at the equator. And the new cycle begins when again, the sunspots start appearing at higher latitude. And that happens almost every year and so on. And since the pattern looks like a butterfly, it's called the butterfly diagram of the sun. Okay. Now, we know that the sun has magnetic field, and that is essentially, I told you, the G-Man effect changes the spectral shape as well as the polarization. So this is a slit here, and you do the spectroscopy. What you find that there is one line here which shows as soon as you hit the dark region, the darkest region here, you start seeing that the line is, one line has started showing 3 lines, and that is the G-Man splitting. Now, using this, you can measure the magnetic field and the polarization. Then you can take different direction of the magnetic field, and you can infer what the magnitude is and what the direction is by taking these different combinations of the polarization. So you have IQ, and you take different, so Y is intensity, then these two are giving you the linear polarization, and this gives you circular polarization. And by taking this, the circular polarization will give you a sort of the line of sight component, whereas Q and U will give you the horizontal component of the magnetic field. Now, once you do that, then you can create magnetic field map on regular basis. So this is done from SOHO was a satellite, and MDI, Michelson Doppler imager, was an instrument, and that measured magnetic field at each pixel. And you can see that the magnetic field also appear to be in the similar latitude range where the sunspots, the strong one at least, and that is because the magnetic fields are stronger in the sunspot region, and you can measure at each point. Now once you do that, then as we did for sunspot region, we noted their location. We can also do with the positive field and magnetic field, and we can create a butterfly pattern. Now, this has been possible only since 1975. What you see, if you compare that, 1975 will be around here, right? And that's where this starts. When you go to 1980, which is in the middle of the cycle, but if you go around 1975, 76, 77, that's where your cycle begins, this one. And what you see that there is 2 colors here. The yellow is positive polarity and the blue is the negative polarity. At this time here, the pole is negative and the north pole is positive. And the appearance of the magnetic field is such that it is opposite direction in the north than in the south, right? So in the north hemisphere, what you have, the blue is appearing as a trailing, whereas the yellow is leading polarity, whereas completely opposite in the southern hemisphere. And as and when the cycle is progressing, one polarity is migrating towards the equator from the north, and the opposite polarity is migrating from the south towards the equator. Whereas this blue here is migrating towards the yellow on the pole, and this yellow is migrating towards the blue on the pole. And after about 11 years, this has all changed to blue, and this has all changed to yellow. So the sun's polarity has been flipped, right? And now, since this is yellow, this becomes blue after 11 years, then yellow. And this guy here, the orientation here also changes. Now the blue migrates towards the pole in south, and yellow migrates towards the pole in the north, right? And then the cycle continues, okay? And that is what is called the solar magnetic cycle. And the magnetic cycle changes by 22 years, because cycle, we call it when you start and get back to the same. So this changes to 11 years, and then in 11 years, it just goes back to the same polarity. And that's what called the solar magnetic cycle. Now, depending on the magnetic cycle you have, if you just compare how many CMEs, how many flares are there in different years, and how does this compare with the magnetic flux you see on the solar surface. So this line here, is called the number of sunspots. The stars here are the magnetic flux, and the triangles are the number of ejections, eruptions you see. And what you find, they are very nicely all correlated with the number of sunspots and number of CMEs and the magnetic flux on the surface. This is essentially to show you how actually this happens. So one polarity, other polarity, they have start appearing different way. They eventually, after 11 years, they go through this process. After 11 years, they change the polarity, and then it keeps going on and on. When you measure the magnetic field during solar maximum, that means when you have the maximum number of sunspot, as you can see, the sun surface is full of strong magnetic field regions. Whereas if you go towards the minimum, that's in 1996, it just looks salt and pepper, and there is no large scale magnetic field present. And if you take this again, eclipse observations, artificial eclipse observations during minimum and maximum. So in the minimum, as you can see, there is only two structures here, very faint structures here, there. And the number of eruptions happening is very small. Whereas if you compare with this, you could have about 10 eruptions per day when you have a lot of magnetic field on the surface of the sun. If you compare that with what you see in X-ray, so this is a magnetic field image at the solar maximum, then going down the activity, and then solar minimum, and then it starts increasing, and then it comes back to solar maximum. And if you do X-ray imaging of that, then what you find that the X-ray changes almost accordingly with the way the magnetic flux changes. So the whole high energy radiation, which is coming from the sun, is all related because of the presence of the magnetic field. How it works. So the idea is that there is a differential rotation and convection, right? So convection, I showed you, there is a convective blob of plasma, which is coming from inside to outside. But also you have the differential rotation. As I mentioned, that the pole rotates slower than the equator. So what happens is essentially you have the seed field, which is going from one pole to the other. And because of the differential rotation, the center part moves faster. And if you imagine there are millions and millions of these flux tubes, eventually you form a toroidal field. And then the toroidal field eventually will have very strong magnetic field. Now, if you compare that the magnetic field inside is large than outside, then the density has to be very small for the pressure balance to remain, right? And if that happens, then it's like buoyancy, right? Because if you take a balloon inside swimming pool and blow, then the balloon will come out because the balloon grows, and because of the buoyancy, it just comes out. In a similar way, the flux tube will have very strong magnetic field, so very small density, because the inside pressure and outside pressure has to be equal, and therefore the flux tube becomes buoyant and it just breaks out on the surface of the sun. And when it breaks out like that, it forms sunspots. And depending on which direction it is going, if it is going this way and going inside, it forms two different polarity, because the flux here will be going in plus and then going down in minus. So those are the two polarities formation. These are the equations I just mentioned to you, that this is the momentum equation and this is the induction equation. And these two together deal with how actually the plasma flow will interact with the magnetic field, and then the magnetic field will interact with the plasma. We essentially bring out everything together as magnetic flux tubes going up and forming sunspots. This is just showing the buoyancy. So pressure outside, it has to be equal to pressure inside plus B square over 2 mu, right? That's the B is a strong magnetic field. So if this has to be equal, if this is these are the two gas pressure, then the P inside will be, if the density is not same, then it will be, inside will be lower than the outside. And therefore, this will become buoyant, and then this will form these kind of loop system. So this is the loops you see in the upper layers of the atmosphere, but these are the two on the surface. They will appear as sunspots. Okay. And then this is just the creating the sunspots, but then how actually you feed in back again. And there are various theories about how actually you convert this poloidal field again into the toroidal field so that it just goes back into the convection zone and comes back. And one theory is this here, that you have the emergence of these flux tubes, and then there is a conveyor belt which actually migrate the fields from the equatorial region to the polar region, and then it seeps in from the pole, get back at the bottom of the convection zone. And since that is a very strong shearing layer that can amplify the field very strongly, and then that becomes buoyant again and comes down. But all these processes are not fully understood, and there are a lot of research going on essentially to figure out that what kind of dynamo works. Some people now say that there is a dynamo also in the upper layers of the atmosphere because of a lot of turbulence going on in the upper layers, in the photosphere itself. And there are a lot of magnetic flux is being generated over there, in addition to these large scale flux tubes. So this is an animation which is put together by SESI group at ISSAA Kolkata. And what essentially tells you, it is, let me just start from the beginning. So this is going from the sunspot observation to opening up. So it will open up and go into the convection zone. So this is at the bottom of the convection zone. You see a lot of shearing layer. And this is the toroidal flux, which is forming. They become buoyant and they essentially break out like this on the surface, and they form the number of sunspots. As and when they break, you see this number of sunspots are increasing with time, right? So more of them, they break out, they form this number of sunspots, and then it just goes down again with the solar cycle, then it increases again, and so on and so forth. Okay. Right, so this is now time to take questions. Let me see whose hand is raised. Astha Chaturvedi, can you unmute and ask?
Am I audible, sir?
Yes.
So what is meant by merging of magnetic field lines in photosphere?
Can you repeat the question, sorry?
What is meant by merging of magnetic field lines in photosphere that you mentioned in context to the sunspots?
Merging of the field lines in the photosphere?
Yes, sir. You mentioned it in context to the sunspots.
Merging of the field lines, I didn't say that. What did I say?
In the very first picture, yes, I guess
this one?
32.
Oh, this one. Okay, all right. Yeah, this. Can you see my screen?
Yes, sir.
Yeah. So this one here. So what essentially? Hold on a sec. Let me put the charger on my laptop. Yeah. So the way it is understood is like at the center here, you have the magnetic flux, which is vertical almost. Okay. So it's like, can you see my hands?
Yes, sir.
Right. So if you consider a flux tube, which is very vertical within this, but consider that some of them are going vertical, but on the outer parts, right, the field lines are going like this, right? So the vertical fields, and then further away you go, the field lines are opening up, right? And when you go in the outer regions, then they just go up, and then they touch the photosphere and merge into that, right? So that is one model where they have explained that how actually you form different kind of magnetic features which we observe.
Does anything significant happen when they touch the photosphere?
Well, you start seeing different polarities of the magnetic flux. So if the flux is going like that, and touching the photosphere. So while the same flux is going up, you should be at this location, you will see a positive polarity. Okay. But when they're going and touching it, then you'll start seeing a negative polarity.
Okay, the polarities.
Then they come out again. The polarities will be changing. So you might think that this is a new flux tube, but essentially it's the same flux tube which is going and touching it, and it's giving you a false impression that it's a new flux tube. You understand what I mean?
Okay. Thank you, sir.
Okay. Kaushik Panja, you want to unmute and ask?
Yes, sir. Am I audible?
Yes.
Yes, thank you, sir, for your lecture. Sir, my question is about that coronal graph image, the artificial coronal graph, maybe slide number 41, very possibly.
Yeah.
Yes, sir.
Yeah.
What is this black line? This total dark line? What
that is just the instrument part. It's just a hand which is going out and holding that. It's a sort of stand for the coronagraph. It's not solar structure.
Okay. Thank you, sir.
Okay. Zunix Sengupta, can you unmute and ask? Right, he's not there. Sandeep Kumar Dubey.
Hello, sir. Am I audible?
Yes.
Sir, actually, I have two questions. So the first question is there a relation between the solar oscillations that are happening in sun and hitting the coronal region? And the second question is, so the strength of magnetic field can be splitting, right? How do we connect its polarity? Whether it's, strength can be split by G minus polarity.
Yeah. So there was a lot of research going on looking at different oscillation mode, which is there on the solar surface, like P mode and sound waves. What we figure out is that the energy they carry, first of all, most of it just gets reflected into the chromosphere. So some part dissipates, and some energy is, of course, deposited in the chromosphere. But the total energy needed for heating the upper atmosphere is not enough. Our total energy given by these waves are not enough to compensate for the total energy needed for heating of the atmosphere. Okay, so it's just very small in comparison to total energy you need. The second question relates to direction of the magnetic field, right? That's what you said. So you can infer the strength of the magnetic field just by looking at how much the line is splitting. But the direction you can look at by doing the polarization measurement. Okay, so if you look at the Stokes polarimetry, if you measure all these Stokes parameter I, Q, U, and V, the linear polarization will be giving you the horizontal component of the magnetic field, where the circular polarization, depending on if it is the left-handed circular polarized or right-handed circular polarized, it will give you either the field is coming towards you or the field is going against you, away from you towards the sun. So from there, you can infer all the directions of the magnetic flux or the magnetic field. Okay. Kunwar Alkendra Pratap Singh, is that the same Alkendra whom I know?
Hello, can you hear me? Hi.
Hey, Alkendra.
Hello, hi.
You should be giving this lecture, not me.
Yeah. So thank you for a wonderful talk. I was just looking into the movie the nice movie that you showed on the LASCO movie, in fact. So on the right hand side, it was some solar minimum, and left hand side, it was some solar maximum. So
this one.
Yeah, exactly. So on the right hand side, we have this near solar minimum situation. And if we just compare these two movies, then the impression that I get is that on the right hand side, which corresponds to the solar minimum, there are some kind of very outstanding CMEs popping out from the solar disk. Mm-hmm. So could you comment on the link between, or the possible link between, the solar minimum or near solar minimum with the powerful CME or space weather events?
Yeah, so that has been a known problem, and the way people understand it, when the sun is going towards the solar minimum, although this is in the rising phase of the solar cycle, you see much more stronger CMEs when the sun is going from minimum towards the maximum, because the sun actually tries to get rid of all the magnetic energy it has, which it has generated during the solar maximum time. So you start to see a lot of very powerful CMEs during the decline phase of the CME. Of course, in the increasing phase of the solar cycle, you could also have sporadic active regions which can come up very strongly and give you some really strong CMEs. And there have been observations like that. They become nicely observable in the LASCO images is because the background is not that strong, as you can see during the solar maximum, because during the solar maximum, you see all these streamers like kind of isotropically distributed around the sun.
Right.
Whereas during the solar minimum, it's just because of dipolar configuration sort of. The poles are much more well defined in the minimum, and the streamers are very localized towards the equatorial belt, right? So the background is also not that large. So that's why they appear very nice and very distinct also. But we have had many cases, and sometimes, as you mentioned as well, during the decline phase, these CMEs could be very, very strong, and they could have much more severe effects than CMEs during the maximum phase. It's just because there's a lot of flux and sun wants to get rid of it.
All right, thank you so much. So this will help me in finding some interesting data sets as well. So okay.
Of course, yeah, sure. Thank you. Kaushik, you have further questions? Okay, let's go to Ayush Garg. Ayush, can you unmute and
Hello.
ask?
Is it audible?
Yes.
Hello, sir. In this very slide, there is a small circle in the center. Is it the core, or how is it drawn?
This one?
Yeah. How is it formulated?
Yeah, that is the disk of the sun. That is the size of the sun. And that is the occulter. This is the artificial moon.
I'm sorry, sir, I didn't get you. The size of sun and moon during the solar eclipse, they cover the entire disk.
Exactly. Right. So the angular size becomes the same, right? That's how you create the total solar eclipse. But here, so if you create a smaller occulter, so this is called occulting something. If you create a smaller occulter, then you will not see anything like that. But you can create as big an occulter as you want, because the intensity falls off very sharply, okay? So if you want to see further out in the sky, while the sun is up there in the solar direction, then you have to block the sun and its intensity as much as possible. So the larger occulter you build just to create a bigger moon so that you can see faint structures around in the interplanetary medium or in the heliosphere.
So how does these occultations can be formed?
Sorry, go ahead.
How does these occultations can be formed from the Earth's surface?
No, so this is not done from the Earth's surface. You can do it from Earth's surface also, but observations will be very limited. This is done from space. So you put a telescope there with an occulter, and you launch the occulter and let the only light fall from the outer side on your telescope.
Okay. So our Hubble Space Telescope does this, or there is any specific telescope that captures the sun?
Hubble Space Telescope doesn't look at the sun. No? Hubble Space Telescope hates the sun. It doesn't care about the sun. So that's why it's a nighttime astronomy instrument. No.
Okay. Thank you.
All right. Saikham Pravas Singh, you want to unmute and ask?
Hello, sir. Good afternoon, sir.
Hello, tell me.
Am I audible, sir?
Yes.
Sir, we find that sunspots region are relatively cold as compared to its surrounding.
Yes.
What can be the temperature of the sunspot region, sir?
Sunspot regions. You're asking the temperature of the sunspots, is it? Hello? Can you unmute and tell me what are you asking? Temperature of the sunspot? It is something around 4,000 degrees. Okay, he has left. All right. Alkandra, you have further comments to make, or just hand is raised?
So yeah, nothing to comment. So thank you so much. Yeah.
Okay, thanks. Saikom, you're back again. So you wanted to know the temperature of the sunspot, right?
Yes, sir. Yes, sir.
Yeah, so that is roughly around 4,000 degrees.
Please repeat.
It's 4,000 degrees roughly.
Okay. Okay, sir. One more question, sir. Sir, how is the number of sunspots changing with time? Sir, how is the number of sunspots changing with time?
With time, yeah. I showed you this plot. Can you see my screen? Can you see my screen? So you see that the number of sunspots in the beginning, there is none, and then it increases and then it decreases. Right? So it could be one sunspot at a time, and then it could be 100, and then it comes down, and so on. Yeah, it doesn't go to 100 on the disk.
So what is the main mechanism?
Main mechanism, I thought I explained it to you. Were you not there? You can listen to the video later on. It's something called a dynamo, which works here. We looked at these. Were you there when we talked about this slide?
Okay, sir. I missed this one. Let me see later.
Yeah, you can look at the video.
Thank you, sir. Thank you.
No problems. Zunik, you have further question? What? Can you unmute and ask? And if not, then lower your hand, please. Okay. Kaushik?
Yes, sir. I have another question.
Okay.
Yeah, sir. My question is there any relation between the angular velocity of the sun and with the number of sunspots or the solar winds? Is there any relation?
I don't know. Why should there be a relation?
Just in case, actually, in that another slide, you showed that the sun is rotating in a direction, and the number of magnetic field that is producing is just getting generated and getting directed in different directions. That's why I thought perhaps there should be a relation with angular velocity and number of sunspots.
I don't know if somebody has done, if anybody has done this work. Alkandra.
What was the question? Sorry, I couldn't follow the question.
The question was is there any relationship between the angular velocity of the sun and the number of sunspots?
Okay, so angular velocity, when you talk about, basically you are trying to relate it with the differential rotation.
Correct.
Yes, sir.
So in the complete, so this is the basic model. So the right now what you are seeing on the screen is the basic layout of the whole thing. So what is happening is that your magnetic flux tube is coming up from below, and then because of this differential rotation, you can see your magnetic fields twisting and all that. Apart from this differential rotation, so yes, differential rotation of course plays an important role because in dispersing the magnetic field from one place to the other over a longer time scale. But also we have to keep in mind that apart from the differential rotation, which is a kind of a flow, there are other kinds of flows such as meridional circulation and things like that, that also comes into picture. And then in totality, there is a kind of a loop or a cyclic process that comes into picture, and then that gives rise to recursive or the cyclic magnetic field evolution on the sun. So that would be my answer. Yes, differential rotation does play an important role.
Okay, so thank you, sir. And is there any straightforward relation that if with the angular velocity, if the angular velocity rises, then the sunspot will rise in number or anything like that, or it remains steady?
Okay, so the temporal variation in the differential rotation or the meridional circulation or anything like that certainly will have some important role to play on the solar cycle. So there are works by Professor Arnav Rai Chaudhary and Professor Dibyendu Nandi where they have studies variety of these kind of processes. So one can follow into that. So there are regularities in the solar cycle, there are irregularities in the solar cycle, and these have something to do with the time variation as well. So you may like to see those works by Professor Chaudhary and Professor Nandi.
Okay, thank you so much, sir. Thank you.
Thank you, Alkendra. So if you don't know, Alkendra is a professor of physics, assistant professor at Banaras Hindu University, and he works in solar physics, and he focuses on various theoretical problems in the solar atmosphere, as well as helioseismology to some extent, Alkendra, isn't it? Okay, who else had a question? Astha, you have a question?
Yes, sir. So what is the reason for the spike around 1960?
1960?
In the number of sunspots.
Hold on a sec. Oh, here?
Yes, sir.
Yeah, because the sun was more active during that cycle. So there were more number of sunspots.
Can we predict that maximum?
Huh?
Can we predict that maximum?
Yeah, that's what people are trying to do. As Professor Alkendra Singh also mentioned, there are two groups in the country, or like it's the same group. Dibyendu Nandi has been trying to predict that how strong that cycle is going to be. But the final answer is still not clear that how well or how bad you can predict. The models given by Professor Arnav Rai Chaudhary did predict the last solar cycle very well. We will have to see how that prediction is going to match for the next solar cycle. So yes, people are trying to do that. Some successfully, some unsuccessfully, but it has to be monitored with time that how well they could do it for cycle after cycle, so that we can say by confidence that yes, this can be done.
And so one more thing, is the magnetic field of the sun related to the angular rotation? Because the flipping of magnetic field lines is responsible for the sunspot cycles, right? So if they are related in some way, then just we
could be, yeah. So as Professor Alkendra mentioned, these problems are being studied currently by different people, and you may want to follow work by Dibyendu Nandi and Professor Arnav Rai Chaudhary to see what they have done. So there might be some effects of the angular rotation, angular velocities, and how actually that affects on the switching as well as the whole solar cycle that might be there.
And sir, about heating of the corona, and just I have this very loose thing that it might be possible because of the extra momentum transfer due to the violence and activity taking at the surface, which might cause the particles which are present in the coronal atmosphere to be heated up at the very high temperature. Like, is there anything like that or any theory?
No, these explosions happen on the surface of the sun, and they do, of course, heat the plasma up into the upper atmosphere and in the corona. But the problem is that the corona is always at 1,000,000 degrees, but the explosions do not happen all the time, right? So if there are no explosion for months, but the plasma is still at 1,000,000 degree, then how do you explain that by explosion? And that is the problem, right? So then people have come up with ideas that, there may be many, many small explosions happening. But the way it turns out that if we all go down to that, the number of explosions and the number of and the amount of energy we would need, it will be very, very large, and they will be happening all the time at a very small scale, which we don't resolve yet from our telescopes. So that is a possibility, but observations have not shown it definitively yet.
Okay, sir, got it. Thank you so much.
All right. Last question, Anushka Tilekar. Can you unmute?
Yes. Hello, sir.
Yes.
So my question is, just like the sun has sunspots, all other stars has the sunspots as well. So when we look at any different star for observations or for studying, so is there any way we can trace back the history of those sunspots for that particular star? Just like when we look at a new planet, we look for the asteroid impacts and craters, which in turn gives us the information about its geodynamic and geostatic activities over the years. So just like that, if is there any way we can trace back the activity or locations of the sunspot, the past sunspots for any star?
Well, those other stars are so far away that we cannot detect the starry spots. There are some limited number of observations where they have shown that starry spots are there, and one can map them, but we don't have enough observations going in the long history to look at the historical records of sunspot, because all the stars, they look like a point source, right? You don't resolve the structures on those, isn't it? So you don't really know where the sunspot, what the starry spots are, and so on. And that's why that's probably not feasible. Okay. Maria Rose just woke up, but let's take this, and that's the last. Maria, unmute and ask.
Sir, can you hear me?
Yes.
Sir, you talked about the rotation of the equator going faster than the poles.
Yes.
How can it happen? Then about the stability of rotation. Can you please explain it?
Say it again. What?
The poles are rotating slower than the equator.
Yes.
Then about the sun existing there, its shape and all. How is it possible equator rotating faster than the poles?
Yeah, so most of the stellar objects, they show such kind of rotation, and there's a good number of articles and research done on the stability of differentially rotating objects. So you could look at those and try to understand how do they do the stability analysis. Okay. There are a lot of literature available online as well as in different books, which you can figure out. It's more like a classical mechanics question than a solar physics question. Okay. All right. Thank you very much. And I hope you enjoyed about listening about sun. And I wish you good luck with the rest of the courses. Thank you, Sagar. I will log off then.
Okay, sir.
Yeah.